Hi everyone, I'm Rachi. I'm a researcher at Microsoft, and today I'm going to talk about Predictroute, a toolkit for predicting network paths. This work is in collaboration with David, Philippa, and Andrew at UMass Amherst. I'll begin by describing what we mean by network paths here. Network paths are the paths taken by traffic from a source host to a destination host on the internet. These are often measured using a diagnostic tool called traceroute. For example, a traceroute issued at the source A towards the IP address of the destination P would expose the path from A to B to C until P. These network paths can be aggregated at different granularities depending on the use case. For example, hops in network paths could be BGP routed prefixes or even autonomous systems or ASs. The goal of our work is to predict network paths between arbitrary sources and destinations on the internet. Before I describe our approach towards doing this, I want to emphasize that predicting network paths is useful for a large variety of applications. First, network paths are crucial for performing effective network diagnostics. Network operators need to answer questions like, how has this client's path changed from what it was yesterday? Or, how long is the client's path in terms of AS hops? Second, network paths are important in gauging the threat of routing attacks by network adversaries. In this case, we want to ask questions like which autonomous systems are encountered by clients on both the forward and reverse paths. And finally, the knowledge of network paths is used to place critical infrastructure that needs to be on the path of client traffic. Given the importance of network paths for diagnostics and a variety of other applications, one might wonder, why don't we just measure these paths on demand using tools like traceroutes? There are several reasons why on-demand measurements do not work for the applications that we just discussed. For example, on-demand measurements require vantage points to be available within the source AS or prefix. However, vantage points are not ubiquitous and can be hard to come by. Second, network paths change due to several phenomena like route changes and link failures. So by the time you get around issuing on-demand measurements, the path that you were interested in might have changed already. And finally, measurement platforms available today have a notion of a measurement budget. This means that as users of these platforms, we cannot issue unlimited number of measurements. Constraints on the measurement budget decide when and how many measurements can be run on demand. So hopefully, I have convinced you that the knowledge of internet paths is important for a variety of applications, and on-demand measurements can be either impossible to make or insufficient. So in this work, we develop a system that predicts paths on the internet. Before I describe the key techniques that we use in this work, I want to talk about why predicting network paths is hard. Network paths change over time. So for example, between the same source and destination, at one point in time, the measured path may go over the hops B and C. But at another point of time, it can take a shorter or more direct path through D. These path changes can happen due to changes in routing policy or router and link failures, and even load balancing across network hops. Therefore, we want to predict network paths that are subject to stochastic and time-variant phenomena. To do this, we capture routing behavior by training probabilistic models of routing and use maximum likelihood estimation to predict network paths from these models. In the next few slides, I will give more details about these methods. So like I said, we want to train probabilistic models of routing. To train these models, we use a corpus of public trace routes. Some of these trace routes are available freely on public measurement platforms like RIPE-Atlas and CADA-ARC. However, these trace routes might not be sufficient to train the routing models. So we also run selected trace routes ourselves to gather more training data. And I will say a bit more about how we select these trace routes to run in just a few slides. From the corpus of trace routes that we've gathered, we group all traces towards the same destination prefix. So for example, all traces to the prefix P are grouped together. These traces are from different sources A and B. And at this stage, we've aggregated the traces to a sequence of hops, where each hop is a BGP prefix. But it could also be at a coarser granularity, like an autonomous system. In fact, Predictroute allows the flexibility to select the granularity of predicted paths to be either at the prefix or the AS level. We then combine these sequences of hops to infer connectivity information between them. I will note here that only the trace routes towards a destination prefix are used for inferring connectivity towards that destination prefix. And this is because previous work has shown that routing on the internet is largely destination-based. Here is what the process looks like at a high level. We start with a sequence of traces from different sources towards the same destination prefix. We then combine these sequences of hops and infer the connectivity between the hops to build the topology of the per destination probabilistic model. Now that we've inferred the structure of the probabilistic model for all prefixes in our training dataset, we make the first order Markov assumption. This means that the likelihood of traffic taking a next hop depends only on the previous hop. For example, if we were inferring the likelihood of traffic taking the path from source A to C to E towards prefix P, it would be the product of these conditional probabilities that are listed on the slide. Since we've made the first order Markov assumption, the conditional probability of taking a next hop only depends on the previous hop. This assumption is derived from both domain knowledge and practical considerations of implementing the procedure. And we present a detailed discussion for it in the paper. Now, all we need to do is to infer the conditional probabilities. We use the known technique of maximum likelihood estimation to estimate these conditional probabilities. Let me show a simple example to demonstrate this process. Let's assume that there were 6 trace routes towards P that took the path from C to F, and there were 4 trace routes that took the path from C to E. So the probability that traffic towards P would go over the CF edge is 0.6, and the corresponding probability of going over CE is 0.4. In a similar manner, max likelihood estimation helps us figure the transition probabilities of the first order Markov chains. Once we've trained the Markov chains, the problem of predicting paths from the routing models is that of inferring the most likely sequence of states. To predict the path from A to destination prefix P, the start state is A and the goal state is P. We want to infer the most likely sequence of states from A to P. But remember that if we do this in a brute force way, there can be an exponential number of paths between A and P. So we cannot perform a brute force exploration of paths to find the most likely one. Instead, we use the polynomial time Yen's algorithm to compute the k shortest paths between A and B. We substitute the negative log of the conditional edge probabilities as the weight of the edges for Yen's algorithm. This allows us to get the k most likely paths between A and B in an efficient manner. For example, the CF edge is more likely compared to the CE edge based on the maximum likelihood estimates that we've learned. Since all other edges in this example have unit probability, the probability of path ACFP is higher than the probability of the path ACEP. And thus, this path is the most likely one between the source A and destination prefix P. Now that we've discussed how Predictroute predicts network paths, I want to revisit the problem of gathering sufficient training data to build the Markov chains. As I mentioned before, we start with public trace routes that are freely available through measurement platforms like RIPE Atlas and CADA-ARC. However, these trace routes can be sparse and intermittent, offering us a partial, low-confidence view into the structure of the destination-specific models. At times, these public datasets can also be stale, consisting of traces that ran days or even weeks before we use them. We use the public data to build partial and low-confidence destination-specific routing models, like the one in this example. While these topologies are built from stale and sparse measurements, we can use them to infer which measurements should be run to improve our visibility into the network topology. We launch measurements from RIPE Atlas using a constrained measurement budget. For example, given the partial topology here, running a measurement from the source A can expose two nodes, nodes E and C, whereas running a trace route from B is going to expose just one node, which is node B. We use this information to decide how to maximally explore the network topology using the constrained measurement budget. We show that the set cover problem reduces to this problem of efficient topology exploration within constrained measurement budgets. More details on this are available in the paper. I will wrap up this talk with a quick look at the results. In this work, we developed Predictroute, a toolkit for predicting network paths. Predictroute accurately predicts network paths. We find that the predicted paths differ from measured paths by at most 1 AS hop 75% of the time. To train its routing models, Predictroute efficiently explores the network topology. Predictroute's method of topology exploration discovers 4 times more AS hops as compared to other strategies. And finally, we are releasing the code base of Predictroute along with a proof of concept implementation as part of this work. Details about the results and links to the code are available at predictroute.github.io. Thanks, and I'll be happy to take any questions.